Okay, so let's get started for the final talk of today. It's a great pleasure to introduce Alberto Lerda, who's going to tell us about strong coupling expansions in n=2 supersymmetric theories. Thanks, Alberto.
Thank you very much, Gerald. And I would like to thank the organizers for giving me the opportunity to speak at this workshop. Today, I would like to discuss some properties of the strong coupling expansions in supersymmetric gauge theories in 4 dimensions. And my talk is mainly based on the content of a few papers that we have written recently in collaboration with my colleagues in Torino. But of course, it builds on a very vast literature, some of which I'm going to refer during the talk. This is more or less the plan of what I'm going to say. I will start with some introductory remarks and a brief review of some known results. Then I will briefly discuss the localization procedure, that is the technical tool that we use to compute the various observables. And then I will move to discuss the strong coupling expansions of these quantities. And finally, I will present my conclusions and give some perspectives for the future. So I think that we all agree that finding exact results in an interacting quantum field theory is a very difficult problem. And it's also very difficult to study the strong coupling regime of an interacting quantum field theory, simply because the usual perturbative methods cannot work, obviously. However, when the theory possesses a high amount of symmetry, significant progress can be made. And this is the case of the n=4 super Yang-Mills theory in 4 dimensions, which is the maximally supersymmetric theory, gauge theory in 4 dimensions, where over the years many exact results have been obtained and many interesting physically relevant quantities have been computed. They include the 2 and 3 point functions of protected operators, the vacuum expectation values of Wilson loops, the cusp anomalous dimensions, the Bremsstrahlung functions, integrated correlators, and other objects. And the main tools that have been used to compute these quantities are integrability, localization, and holography. So let me just remind a few basic facts about what happens in this n=4 super Yang-Mills theory, which is the simplest gauge theory that we have. It's a theory in 4 dimensions. It's a gauge theory, and its field content is given here. There is a vector. There are six scalars and 4 chiral fermions, and all of them are in the adjoint representation of the gauge group, which I take to be SUN. And this theory has a standard action. This is the usual Yang-Mills term for the vector. This is the kinetic term for the scalars, plus a quartic coupling, plus there are the fermionic terms. And here the gauge coupling I've written has n, where n is the number of colors divided by lambda, where lambda is the 't Hooft coupling, which I am going to consider fixed in the limit in which n, the number of colors, goes to infinity. That's the large n limit about which we heard in the very first talk in this workshop on Monday. This theory also possesses an holographic dual, which is a gravitational theory in 10 dimensions in space-time, which has a factorized structure of anti-de Sitter 5 times a sphere S5. Among the simplest observables that we have in this theory are the local operators, local gauge invariant operators, which we can construct by taking simply a product of the scalar fields. So for example, here I take k scalar fields, I multiply them, I contract the indices in order to make invariant quantity, I take the trace over the colors indices, and I have a local operator, OI, at point x. These are primary operators in this theory, which is conformal, and the conformal dimension is just the number of powers, the number of factors of scalar fields. Once you have these operators, then an interesting quantity that you may compute are the correlation functions. And the simplest one is the two-point functions between two operators, one at point x and one point y, or the three-point functions in 3 different points. Conformal invariance fixes the space-time dependence of these functions, and the only thing that remains to compute is the coefficient that appear in the numerator of this expression. That is a function of the number of colors n and of the coupling constant. It happens that if you take the planar limit when n goes to infinity with lambda fixed, which is the 't Hooft limit, then these quantities actually simplify enormously. Well, these two-point function coefficients and these three-point function coefficients clearly depend on the way in which you normalize your operators. So in order to get rid of these normalization ambiguities, what people usually consider are the so-called structure constants, which are simply the three-point functions divided by the square root of the two-point functions. These are part of the conformal field theory data that you are interested. And in the planar limit, these quantities actually do not depend on the coupling. This was a remarkable result obtained at the end of the 90s by these people. So here we have a quantity which has an intrinsic meaning in the theory, which remains the same all the way from weak coupling to strong coupling. You can compute it at weak coupling using standard Feynman diagrams, using standard field theory perturbative methods, and you get this result. On the other hand, at strong coupling using holography, you can compute it using Witten-like diagrams, and you get the same answer. So that's a very simple example of a smooth, weak, strong coupling interpolation. It's a quantity which stays constant all the way from 0 to infinity. And even if it looks like a trivial result, this is actually quite remarkable, because at weak coupling, you do a perturbative calculation using Feynman diagrams. At strong coupling, you do a completely different calculation using gravitational rules in anti-de Sitter space-time. You propagate graviton modes, so it's a completely different calculation, but it yields, in the end, the same result. And indeed, this paper by Leeming, Waller, Angamani, and Seiberg in '98 gave rise to a lot of activity. And it is the first real check of this ADS-CFT correspondence. A less simple example is given still in n equals 4 super-Young Mills, is given by the vacuum expectation value of the circular Wilson loop. So you have now not a local operator localized at the point, but a line defect. You have a loop in space, and along this loop you compute the path-ordered exponential of the phase. This is in n equals 4 super-Young Mills, so the usual Wilson loop has to be upgraded with a part that contains the 6 scalar fields that was introduced by Maldacena in '98. And now you can take this important operator and compute its vacuum expectation value. If you are at weak coupling, then you can do a calculation using Feynman diagram techniques. This calculation was done by Ericsson, Semenoff, and Zarembo in 2000. And you start computing perturbatively, and you start building, in the large n limit, a series, a perturbative series in lambda. This is the 3-level result. This is the 1-loop result, the 2-loop, and so on. In this limit, there is a huge simplification. So a lot of terms actually, a lot of diagrams actually do not contribute. And you remain with a rather simple expression in the end. If you are interested in the strong coupling regime, then you do a completely different calculation. Again, you use anti-de Sitter's the ADS CFT correspondence, and using the proposal of Maldacena, then you look at the surface that has a boundary on the Wilson loop, and you compute the minimal area law in anti-de Sitter 5, and the same quantity now looks completely different. It starts with the exponential root of lambda, and there are the subleading corrections. Now, these two things are the weak coupling expansion and the strong coupling expansion of an exact formula, which is nothing but a Bessel function. And this is another remarkable result. It's a simple, explicit function of the coupling. And if you expand it for lambda going to 0, you recover the perturbative expansion. If you expand for lambda going to infinity, you start having this expression. An even less simple example in n equals 4 is given by the so-called cusp anomalous dimension that was introduced long ago by Polyakov. And if the Wilson loop is not a smooth curve, but as an angle, as a cusp, phi, then there are divergences that appear in the diagrams, both in the ultraviolet and in the infrared. And you have to regularize them by introducing cutoffs. And the scaling now of the Wilson loop with respect to this ultraviolet and infrared cutoff is given by this expression with a function here that is called the cusp anomalous dimension. There are two interesting regimes in which you can study this quantity. When the angle phi is very small, then this function turns out to be proportional to phi squared, and the coefficient is called the Bremsstrahlung function, which is related to the energy that is radiated by a moving particle in this in space. And again, another interesting exact result given by Correa and Maldacena and Severi in 2012 is that this Bremsstrahlung function is directly related to the vacuum expectation value of the Wilson loop that we saw before by simply the logarithmic derivative, lambda d lambda. And therefore, again, we have an exact expression for this physically interesting quantity. The second regime is when the angle phi in Minkowskian signature is very large. And in that case, the cusp anomalous dimension turns out to be linear in the angle times a function f that now depends on lambda, which is a like cusp anomalous dimension, or also called the scaling function, lambda. And also this function, you can compute it. And you can compute it in perturbation theory using Feynman diagrams. And this is a calculation which was initiated by Polyakov in 1998, and then was upgraded at 2 loops, 3 loops, and so on by Korczemski and collaborators over the year. And again, you start building perturbative expansion that starts with lambda, lambda square, and so on. If you want to compute the same expression at strong coupling, then you have to use the anti-de Sitter CFT correspondence. And here comes an interesting observation by Gupser, Klebanov, and Polyakov in 2002. Now you have to compute in anti-de Sitter space the energy of a spinning string that rotates in the limit in which the spin of this closed string is very high. Then the energy scales with this expression, and the coefficient in front of the log is precisely the same cusp anomalous dimension. And if you do this calculation, which was upgraded by Zeitling and collaborators over the years, then you start having root of lambda, a constant term which goes like 1 over root lambda, and so on. So you may ask, what is the function that interpolates between these? And now it's a little bit less simple, but it's known because quite remarkably, this function f of lambda can be obtained by solving an integral equation called the Beiser-Eden-Staudacher equation in 2006. This is an integral equation, and its kernel can be written in terms of a semi-infinite matrix X, whose elements are a convolution of Bessel functions that depend on the coupling constant. So these people showed that this function f of lambda, which has the meaning of the cusp anomalous dimension, actually is given in terms of this infinite matrix X. It's actually up to a factor of lambda 1 over 1 minus X. So you have essentially to invert this infinite matrix X. And using Kramer's formula, you can rewrite this matrix element as a ratio of determinants. But now these determinants are given in terms of products of Bessel functions, and so you can study the weak coupling and the strong coupling limit. The weak coupling limit is quite straightforward. You simply have to expand the Bessel function for small lambda, and you do the integrals with this weight here, and you recover the expansion that I showed you before. But using the asymptotic form of the Bessel function, now you can study also the strong coupling regime. And that was initiated by Basso, Korczewski, Kutansky in 2007, where they not only found the strong coupling expansion, but also they realized the presence of non-perturbative exponentially small corrections proportional to E2 minus root of lambda. Moreover, a resurgence analysis of this cusp anomalous dimension can be worked out, and indeed it has been worked out by Daniele and Ines a few years ago. And recently there are interesting generalizations of these cusps with tilt angles by Basso, Dixon, and collaborators. So far I showed you 3 examples. A very simple example of a quantity which stays constant from weak coupling to strong coupling, the structure constants of this conformal field theory for these scalar operators. Quite simple observable, which is given by a function, a simple Bessel function. That's the circular Wilson loop that we know all the way from weak coupling to strong coupling. And then a less simple example, which is this like a cusp anomalous dimension, which is known implicitly in terms of this matrix X, which, however, allows us to obtain very explicit expressions both at weak coupling and at strong coupling. All this was in n equals 4, so in the maximally supersymmetric Young-Mills theory. And as I mentioned before, there are many other examples. These are the three, in my opinion, prototypical examples of these features. Now it would be interesting to see whether some of these can be obtained also in less supersymmetric theories, when we have not n equals 4, but for example, n equals 2. The n equals 2 theories are less constrained, therefore things are more complicated. And therefore, this is a very non-trivial challenge. First of all, one may ask whether it's possible to have something which smoothly interpolates between weak and strong coupling, because there are indications that, for example, in the so-called n equals 2 SQCD, so the supersymmetric version of QCD, or in the so-called n equals 2 star, the massive deformation of super Yang-Mills, then there may be some phase transition. So what we see at weak coupling cannot be continued smoothly to strong coupling or vice versa, because there is in between a phase transition, as if the relations that the various quantities satisfying the two regimes are separated like two different phases in thermodynamical systems. However, I would like to discuss a system of gauge theory with n equals 2 supersymmetries in which this does not happen. So in a sense, it is more similar to what we had in n equals 4, but still with a reduced amount of supersymmetry. In other words, I will discuss an example of theories in which one can find exact results where smooth, weak, strong coupling extrapolations are possible, and where one can test these ADS-CFT correspondence in a non-maximally supersymmetric context in a precise and detailed way. And the theories I'm going to discuss are the so-called n equals 2 quiver gauge theories, which are gauge theories with a gauge group which is a product of several factors, in general m, but for simplicity I will restrict to the simplest case, namely n equals 2. So these theories are the next to simplest gauge theories after n equals 4. N equals 4 was the simplest one, and these quiver n equals 2 gauge theories are, so to say, the next to simplest. They can be obtained from the n equals 4 super Yang-Mills with an orbifold projection. We heard on Monday from Riccardo Schiappa the D-brane and the fact that the D-branes support the gauge theory on their work volume. These are the standard branes, not the ones with a negative tension that he was talking about. But we know that these D-branes support on their work volume the n equals 4 super Yang-Mills. And I can take two n-branes and divide them into two groups. And in this way, I obtain precisely my quiver theory. So I have an SUN theory on these branes, another SUN theory on these other branes, and there are the strings that go from one to the other, which form the multiplet, the matter multiplet. So the gauge group, as I said, is a product of two SUN factors. In each node, we have a vector. Now we have just two scalars, not 6 any longer, but two scalars, which I can make in a complex field phi 1 and phi 0 for the two nodes. And these are in the adjoint representation, plus the corresponding fermions. But then I have also fields that go from one node to the other, so in some sense they are matter multiplets. And these matter multiplets are in the bifundamental representation of the gauge group. Given this field content, This theory has a beta function equals 0, so it's a superconformal field theory, also at the quantum level, like n equals 4. And as in n equals 4, I can start defining the various operators. And now I'm considering the simplest ones, those which in n equals 4 were trivial, so to say, namely the local operators and the structure constants. Now, in this reduced supersymmetric setup, even the simplest ones are not trivial at all. And so I consider these local operators, the product of k powers of the scalar fields. Now I have two different gauge groups, so I can take the symmetric or the anti-symmetric combination, and I call these operators untwisted or twisted, because they are either symmetric or anti-symmetric under this Z2 that sweeps the two nodes. And then, like I mentioned at the beginning, I can start computing the 2-point functions and the 3-point functions. This is a conformal theory, and therefore the space-time dimension, the space-time dependence is fixed by conformal invariance. The only thing that remains to compute are the coefficients. And these coefficients are functions of n and of the coupling constant. Again, to get rid of the normalization ambiguities, I concentrate on the structure constants, namely the 3-point function divided by the square root of the 2-point functions. And these are now non-trivial functions of n and lambda, even in the large n limit, even in the planar limit. So how do we compute this function practically in this case? Well, if we are at weak coupling, we can use standard Feynman diagrams. So we can start, for example, at tree level. We have the operators here with k legs, the conjugate operator with k legs. And then we simply saturate these legs with propagators, with the free propagators. That's a very simple exercise to do. Just use Wick contraction, and you get the result. But what happens when you want to switch on the interactions? So you can start having vertex insertions. So the calculation becomes highly non-trivial. And you can do this at the very first perturbative orders, but this is a big effort. So it's something that you can do, but certainly this is not the way in which you can get very far in the perturbative expansion. There is a much more efficient way to compute these correlators using a technique that goes under the name of localization, which essentially reduces the path integrals to finite dimensional integrals in a matrix model. That was proved for this class of theories, in general n equals 2 gauge theories by Pestion in 2007. And this method, which reduces the calculation of these Feynman diagrams to integrals in a matrix model, a zero-dimensional field theory, just numbers, this method applies to the partition function, the Wilson loops, the chiral and anti-chiral correlators, and there is a huge literature on the subject. And the idea is essentially the following. Instead of looking at the theory in a flat space, which is where I was so far, I map the theory on a sphere. Since the theory is conformal, I don't have any problem because the flat space and the sphere S4 are conformally equivalent. So, for example, a point here at the origin of flat space is mapped, for example, at the North Pole, the point at infinity at the South Pole. And now, on this S4, Peston shows us that the path integral over all fields, now in this theory on S4, localizes on a set of points which are captured by a matrix model. So instead of computing a two-point function on flat space, I computed the corresponding object on the sphere, and using Pestun's result, I rewrite everything as a matrix model. More explicitly, in this theory, I have two gauge groups, so two matrices, n by n, they are Hermitian, one for node 0, one for node 1, and according to this beautiful result by Pestun, then the partition function of this matrix model is simply given by the integral with a Gaussian measure, e to the minus a squared for the two matrices, times a factor. The factor is essentially the fluctuation, the one-loop fluctuations around these localized points where the integral localizes, indeed. There is also an instanton factor, but since I am in the planar limit, I can set it to 1 because instantons in that planar limit are exponentially suppressed. And this one-loop factor can be written as a sort of an interacting action for these matrices, which for the theory I am considering is this complicated structure. But if you look at it for a moment, then it's nothing but an infinite sum of terms. All of them are quadratic in the matrices. But of course, there are several powers, so it's not an easy object, but it's very explicit. And the coefficients are just powers of the coupling constant times some Riemann zeta values. So if you want to compute, for example, the partition function, then you simply have to compute this e to the minus s with this measure. So it's something like a vacuum expectation value in a Gaussian model. So this procedure takes the theory on R4, which is the one I'm interested in. Using a conformal map, I go on a sphere, S4. Then using localization, I simplify enormously my calculation and go to a matrix model. And in the end, I have to do integrals over the elements of these matrices with a Gaussian factor. So in the end of the day, I simply have to compute Gaussian integrals. A lot of them, but all of them are Gaussian integrals. So since I had these two nodes, 1 and 0, and the fields phi 1 and phi 0 at the beginning, and now I have translated into matrices A1 and A0, one may think that the operators I had, which were traces of phi 0 to the k, phi 1 to the k, are simply mapped into the corresponding matrix expressions, which I call AK plus or minus. But that's not really correct, because phi is a complex. So phi with phi has contraction 0, because phi talks with its complex conjugate, not with itself. Whereas A, since it's Hermitian, talks to itself. So the contraction here is 0. The contraction here is not 0, so this map is not really correct. And another way of saying the same thing is that the operators in the gauge theory, the original ones, are normal ordered, whereas the operators defined in with this naive map are not normal ordered. In other words, I have contractions with all the ones which have lower dimensions. So the solution, once you realize that, is that you have to normal order these operators. So the right map is that you take the naive expression that the gauge theory tells you, and you normal order it, which means that you have to subtract all the contraction with the operators with lower dimensions. And in the end of the day, it's just a change of basis. Instead of having these operators, you use these, which are a linear combination of the old ones. And these coefficients can be computed explicitly. It's curious to notice that at lambda equals 0, so in the free theory, these coefficients are coefficients of a family of orthogonal polynomials, the Chebyshev polynomials. But when the theory becomes interacting, these coefficients change, but still they keep a structure which is totally under control. So we want to compute the two-point functions for our gauge operators, and we translate it into a calculation in the matrix model with this operator O. And as I said, everything is reduced to a calculation of Gaussian integrals in this matrix theory. Let's do these calculations in the case of lambda equals 0, so in the free theory. So you can see that it's very, very straightforward. So if you give me any function of this matrix A, then the vacuum expectation value is simply the integral with these Gaussian prefactors of this function of A. So, for example, if I want to compute the two-point functions of this operator O, OK, and OL, then I sit there and do the calculations, and in the end, I simply get a number, which is depends on the dimension and on n. So it's OK and OL have these two-point functions. So it's 0 unless K and L are the same. That's something which, from the gauge theory side, corresponds to having the same charge or the same conformal dimension, which is what you expect for a two-point function in a conformal field theory. Also, the calculation of the three-point function is quite simple. Here there is a misprint. This is root. This is m, not n, not 2. But apart from that, it's a factorized expression, and so it's something very, very, very simple. Having this result, you are immediately led to normalize the operators, divide by this number here, so that you can graphically represent this two-point function in this free theory as a free propagator in this matrix model, which I denote by this symbol. Also, the three-point function, here's the right formula with n instead of 2, I can reproduce graphically with these three triple vertex, K, L, and P. What happens in the interacting theory? Because now we are at lambda equals 0. Now I switch on the interaction. In the interacting theory, well, if you take the untwisted operator, those with plus, the ones which are symmetric under the exchange of the two nodes, then surprisingly nothing happens. So even if the theory is interacting, then for this particular class of observables, the interactions do not matter. So you may ask why. Well, the reason is that in the interaction action of the matrix model, actually only the twisted combinations appear. In this particular theory, you have these traces with a minus sign, so the odd ones appear. So to say, the even ones do not talk with the interaction. So when you do the calculation in the interacting theory, when you bring down from the exponent the interaction action, then it simply factorizes. And so it simplifies. This is rigorous in the planar limit. And in the end, the two-point function in the interacting theory is the same as in the free theory for these untwisted operators. And similarly for the three-point functions. But in the twisted cases, namely when the operators are odd under the exchange, then the interaction matters, because the interaction has exactly the same structure as the operators downstairs, so the integrals are not factorized any longer. And now comes the crucial observation, that if you look at this interacting action of the matrix model, and you play a little bit with it, and you change basis, and you go to these operators P, then you realize that it can actually be written in a quadratic form with the matrix X. And the matrix X is given explicitly in the perturbative series in this way, with this zeta function and these factorials. But you can resum this series and write a compact expression in terms of an infinite, semi-infinite matrix L, which again is a convolution of Bessel function. And this was observed by us, also by Gerald and collaborators at the same time, more or less. This is something that you have already seen before in my slides. Not really this function, but something very similar. There was a different weight here, but the structure is exactly the same, just a different function here. This convolution of the Bessel function contains the exact dependence on the coupling constant in the interaction matrix. And that's the key observation that allows us to obtain these observables at any value of the coupling constant. How do we do that? We proceed, first of all, perturbatively. So we want to compute now the two-point function of twisted operators, those with a minus sign. So we start bringing down the interaction action from the exponent. So this is when I take the 1 from here and here. So I get the free term. That's the free propagator. Then I have 1 power of the interaction action, which comes down. So these terms are linear in the zeta functions. And if I compute them, it amounts to insert this matrix X in the propagator. If I go to the next order, I bring down 2 factors of the exponential on the interaction actions. And that means that I have to insert 2 powers of this matrix X in the propagator. So I do repeatedly, recursively this. And so my two-point functions is 1 plus x squared plus and so on. So I formally resum this, and it is precisely 1 over 1 minus x. So this is the two-point function of these operators written in terms of this semi-infinite matrix, and contains this formula implicitly the exact dependence in the coupling constant. I can do the same thing for the three-point function. Things are a little bit more complicated because now you have 3 legs, so you have to dress all legs by these interactions. But in the end of the day, you promote all the 3 legs from the free terms to the interacting ones. And again, also the three-point function can be written in a very compact and precise, but also explicit way in terms of the matrix X. So this is recap. The two-point function in the free theory was the free propagator was 1. In the interacting theory is this d, which is 1 over 1 minus x. And the three-point function was essentially this product of square roots and become the product of these numbers. This is in formulas. And I stress once again that everything is written in terms of this matrix X of Bessel kernel. Some people call it Bessel kernel. But we are not yet at the end of our story, because you may remember that these operators P were defined as the orthonormal operators in the free theory. We still have to do one step further, because we have to promote these operators P, which were normal ordered in the free theory, to the true ones, which are normal ordered in the interacting theory. But again, this is a further step which can be done through the Gram-Schmidt orthogonalization procedure. And remarkably, even after that procedure, one obtains a very compact expression in terms of the matrix X. Now let me spend some time on the properties of the matrix X. This matrix X is a convolution of Bessel functions, and it comes from the interaction action, which was here. And these K and L, the indices of these matrices are both even or odd. So the structure of this matrix is like this. We start from 2 because we are in SUN, so trace of A is 0. So the first term is a trace of A squared. So the index is 2. The first value of the index is 2. Then the odd, even are 0. The odd are non-zero, and so on. So we may reshuffle these entries and define a matrix, the even one and the odd one. And at the end of the day, the two-point function we are interested in for the twisted operators can be written, again, in terms of ratios of determinants of these matrices, exactly like the cusp anomalous dimension, which I mentioned in the n equals 4 theory. These matrices, it's just application of Cramer's formula, so sometimes you have to delete some rows and columns, but this is an explicit result. So now that we have these compact and explicit formulas, then we may ask ourselves, what is the strong coupling limit of these? Well, first of all, the easy question to ask is, what is the weak coupling? Well, by expanding the Bessel functions inside this matrix X in powers of lambda, then it's very easy to generate the weak coupling expansion. And this is extremely efficient because you can go very high. We went up to lambda to 160 just by writing a simple mathematical code that takes a few minutes to generate this. If the value of k is a little bit higher, maybe it takes 15 minutes or so, but nothing, essentially. And we had these very long series with these explicit coefficients. This is the weak coupling expansion. This series has a finite radius of convergence, like all these series at lambda equals pi squared. But having this very long series expansion is very useful because then you can resum, for example, a la Padé, and therefore see how these series look like beyond this point. And this is what we did. Also numerically, this is a plot in which we took these very long series, we resummed it a la Padé, and we plotted for values of lambda over pi squared, which are in the intermediate range. They are quite high, but not still in the strong coupling limit. This is the red curve. This is the Padé resummation. These dots here are the results of a Monte Carlo numerical calculation for this quantity that we did. And we see that when n, the number of colors, increases from 50 to 500, then the dots approach nicely the resummed curve. Here there is also this dotted curve, which is the strong coupling prediction that we obtain from this, on which I will comment in a moment. But we can say that even at this stage, there is a very, very nice numerical agreement. But now the interesting question is, what is the strong coupling limit of this formula? We can do that by analyzing how the Bessel functions inside the matrices X odd or even behave at large lambda. And if you take, for example, the matrix odd, the one which had x33, x35, and so on, and you go to lambda to infinity just by looking at the explicit formula, then you see that in the at the leading term, the matrix simplifies drastically, because most of the entries become 0, and they remain non-zero only on the diagonal, the main diagonal, and the two next ones. This is the leading term. This is something that Gerald and collaborators did, and we also did. This is an important piece of information. The matrix X, when lambda goes to infinity, go like lambda times something. So now we have to compute these determinants. So a very heuristical argument is the following. Since X goes like lambda times the matrix X, then when lambda is large, I can forget the 1. And so I simply have to compute the determinant of lambda S. And I do this both in this expression here. I forget the 1 upstairs and downstairs. I remember that these are matrices with different numbers of rows and columns. And in the end, I get that this ratio goes like 1 over lambda. There is a more rigorous proof of this, in which one does not only get the behavior, but also the proper coefficients, which are reported here. So now we know the weak coupling, but also the strong coupling, at least at the leading order at the moment. Actually, one can do much more than this, because in a recent paper by Beccaria, Korczynski, and Seitling of a few months ago, they worked out a systematic procedure to derive the strong coupling expansion for these determinants, for these matrices, actually for a whole family of matrices, in particular the ones that we are using for these calculations. So now we have not only the leading terms, but also all the subleading ones. And these are some expressions that I wrote. They are very explicit, and you can use them to generate all what you want. There are also some non-perturbative corrections, of course, because these coefficients grow factorially. So using these results, we have our strong coupling expansion for the two-point function. This is the leading term, and these are the subleading corrections. So the two-point function for this particular class of operators is something that at weak coupling tends to a constant times 1 plus lambda, lambda squared, and so on. And at lambda going to infinity, scale like 1 over lambda plus corrections. The strong coupling expansion contains, of course, non-perturbative exponentially suppressed terms, which these people started to compute it, at least the first one, which result from the presence of singularities on the Borel plane. These strong coupling expansions are non-Borel summable, and therefore they need a non-perturbative completion. We extended this analysis to the three-point functions because in a paper of a couple of weeks ago, we proved that the three-point functions are actually related in an exact way to the two-point functions by a sort of a word-like identity, so that if you know the two-point functions, that you reconstruct in an exact way the three-point functions. And so we, given the three-point function, we can also have the structure constants. So we have a formula for the structure constants in this theory, which is true is valid for any value of lambda. If we expand as weak coupling, we recover the naive result, which is the same as, apart from this square root of 2, the same as in n equals 4. But when we go at strong coupling, lambda to infinity, then since these go like 1 over lambda, this derivative become a -1. Well, this is an interesting fact, because this result can be proven quite easily, as it was in n equals 4, by doing a simple calculation using Wick's theorem. Because at lambda equals 0, I just have to use free propagators. So I add my operators, and I contract all legs with free propagators, and I do get, indeed, this result. But if I want to check this, then I have to do a very different, and actually a totally different calculation, and I have to do it in ADS space. And we did it, actually, last summer, and using the rules of Untitled Chapter, we computed the scattering of gravitons, essentially, or better, of scalar fields that arise from the twisted modes of the two forms in type 2b supergravity, and from this calculation we precisely obtain this result. So this is quite remarkable, in my opinion, check of a quantity which, differently from the n equals 4 result, which was the same both at weak coupling and strong coupling, now as an evolution, and this is the lambda equals 0 limit, this is the lambda to infinity limit, and they match with the general result. So let me conclude. I told you that in this class of theories, which I consider these quiver theories, most of the results actually depend on this kernel X, this convolution of Bessel function. The same type of convolution of Bessel function appears, as I mentioned at the beginning, in the discussion of the cusp anomalous dimension in n equals 4. The only difference is the function here. Well, the constant, the overall constant is just a matter of convention, but what is important is the different power. Like for the cusp anomalous dimension, also for the structure constants, which are the important part of the conformal field theory data, one should find in a systematic way the non-perturbative exponentially small corrections, which so far are only computed at the very first one has been computed, and one has to develop a systematic way for computing this one, and fully determine, therefore, the solution at strong coupling. It would be nice to understand whether these non-perturbative corrections are somehow related to the perturbative ones, and check whether the structure constants at strong coupling are resurgent trunk series, like the cusp anomalous dimensions are. The cusp anomalous dimension is. And I think this is doable, because in the end, everything is based on this magic kernel, as Beiser and Staudacher call these metrics. It would be nice also to understand at strong coupling the structure of the corrections from the holographic perspective. I told you that we checked just the leading term by doing an explicit string theory calculation in ADS CFT, but it would be nice to also understand the subleading corrections. At the moment, however, explicit calculations beyond the supergravity limit don't seem to be possible, and so this analysis is a very strong prediction for these string corrections. And from this, you can predict what are the subleading terms which a string theory should reproduce eventually. Thank you very much for your attention.
Thanks, Alberto. So, questions, comments?
Thank you, Alberto, for the beautiful story. First thing, do you have any idea of what this non-perturbative correction should correspond to holographically?
Holographically. And we have not yet understood that. Well, first of all, one has to compute them systematically.
Sure.
Because
but even just
there are
the
just
size,
very, this e to the minus root lambda. No, I don't have an answer to that.
And
maybe worksheet instantons, I don't know.
Yeah, maybe that.
That is certainly something that we plan to study eventually.
And in terms of numbers, do you get anything besides product of odd zetas if you go higher orders, either a weak coupling or a strong coupling?
No, Adweek coupling certainly is a series in which all coefficients are zeta functions or product of zeta functions, and only odd zeta functions in this class of models. At strong coupling, you get, I don't know if I have it, yes, you have again odd. And this structure, by the way, is fully consistent with what you expect from string theory, because you know that the first correction beyond supergravity, this one should correspond to the supergravity approximation. This one should be the first stringy correction. And you know that in type 2b superstring, the first string correction goes like alpha prime cube times zeta 3. And alpha prime cube becomes translated into this 1 over root lambda times zeta 3. The next correction goes like alpha prime to the 5th times zeta 5, and this structure. So these, well, I don't know if the numbers are correct, but at least the structure of zetas and powers matches what you expect from the expansion of the closed string amplitudes, from the Virasoro-Shapiro part of the amplitudes, which is a ratio of gamma functions. And this is, the structure is in agreement with that. The problem is to find exactly these numbers. We computed this leading term, but to find this subleading one is a big challenge from string theory. From this field theory and matrix model approach, then it's not straightforward, but doable, and in fact, it's done.
Okay, well, I think we're, last question, please.
Yeah, so maybe this is completely irrelevant, but so this convolution kernel that you have looks very much like Bessel kernel in random matrix theory after some similarity transformation. So I was wondering, is it possible to hope that these determinants, they satisfy some differential or integral differential equations in lambda?
I think that the paper I mentioned by Beccaria, Korczemski, and Zeitling actually proved that these log of determinants satisfy some differential equations. And from those differential equations, they were able to extract the strong coupling expansion.
Okay, well, I think we need to stop here, save questions for later. Thank you.